A great pleasure to welcome Mads Almassalkhi back to campus after 10 years or so. So Mads did his PhD here actually a few years back. It's traditional to tell a funny story, but I can't think of any. The hard worker who did all this great stuff. So Mads is with the University of Vermont, co-founder of the joint appointment, right, at PNNL, and uses the block M because his name starts with M. So on that note, thank you.
Maybe one funny story, now that people online won't hear it. My first CDC paper, I basically wasn't going to make it because we just had a new baby, and then a tsunami hit Japan, and it was a two-week extension, and we made it. So it's both not funny and funny at the same time. That was a crazy period. That was something else, but it was a good experience. All right, Orlando, and it was in Orlando, which is where the general meeting is this year. All right, so welcome. It's good to see people in this seminar. Lawyers say I have to put this in here. I'm not going to sell you anything today, but I'll talk about the technology behind the company. And I didn't do this myself. There's a lot of good collaborators. Some of them are in this room as well. But I do want to start with a little reflection. So a couple old photos and my first papers. And there's a reason for this, besides the block M being my name. So almost 10 years ago, my second child was born, and I defended 2 months later. So for students, don't do that. That was not very fun, but I got it done. And the other thing that's fun, these are my first 2 papers. This is PSCC and this is the CDC. Title, deal with the topic energy hubs. Just hold on to that word, energy hubs. And hold on to the word Michigan, because when I moved to Vermont, I actually went through a bunch of old photos. And I found this photo of myself in Denmark when I was 12 years old. I don't know if anyone can read what it says on here. That university doesn't exist, right? Michigan University is not a thing, it doesn't exist. I don't know where the shirt came from. I have multiple pictures of myself with the shirt. We never ever talked about Michigan University, and I didn't know what it was until basically I applied in grad school. So things happen for a reason. So Michigan was a reason. Maybe energy hubs was another reason. Anyways, so where I come from right now is the University of Vermont. We have a pretty good group working on energy and autonomous systems with both equity angles, social science, and various forms of technology. We have 3 faculty in power and energy, which is pretty good for a program with 8 faculty altogether. We do really fun research. We have fun both with industry and with federal partners. I'm not going to go through every single project, but basically what we try to focus on is making research that actually matters beyond just the papers. And we've had some success with that. And so we've been writing various papers, and we've conducted various research projects. We've developed some IP. We've worked with industry partners for the last 10 years, or I guess 8 years. As part of that process, we realized that to bring technology from papers to market, we needed acceleration. And so we founded a startup company to kind of do that for us. At first, because it helped with DOE projects, and second, because, well, it started to become a pretty interesting topic. And so I spent a good amount of time working as a co-founder for a small startup company that managed to start out in 2016 and came to a pretty interesting end very recently, and it still is actually finishing up. And so the first paper I wrote was about energy hubs. The startup company that acquired us here this year was Energy Hub. And when Energy Hub acquired our company, Packet Size Energy, we went from having 700 devices in the field running with our technology that we developed in the lab as academics. From 700 devices, the platform that Energy Hub manages is the largest in the US when it comes to the demand response. And it's about 900,000 devices right now, and they're almost at 1 million. That means our technology has reached scale. And so if you work in academia, if you work in research, it's rare that technology can reach scale. They're not running our technology, but our technology finally has access to scale. And so that as an academic has been extremely rewarding. It's been a lot of fun. And so if you talk to investors, we can say, hey, we 1000x'd our technology, not the investment. Otherwise I wouldn't be here. And so it's not just in Vermont that we do cool things like this, it's across the US. And so the green economy is rising, it's growing, jobs, revenues. Climate challenge is following as well. And so my claim here is that inaction is really inexcusable. I guess not really my claim, it's pretty obvious. And I think we all agree that we need to do something about it. And when I spent some time with my friends in Ann Arbor, where we're staying for the week, they talked to me about what happened not too long ago. And so in Vermont, in Michigan, you had 2 million people without power, some of whom did not have power for 5 days, which is extreme. The climate is extreme, this is also extreme. And then 9 days later, it happened again. And so clearly, snow is something we can predict pretty well, kind of know what temperatures will look like, and still this happens. And so there are a lot of solutions, some of them technical, and some of them just common sense. And so if we look for solutions, what we want to realize is that if we find solutions, they will matter if they work. And so to do research and make things work, we need to think about one of the key solutions will be the integration of terawatts of renewable energy. Anyone working in power systems knows that integrating terawatts of renewable energy is a massive power system challenge. And so when I look at power systems, you can think of it, power systems is an engineering discipline, which has really become climate change mitigation engineering, right? We're really trying to have research, having courses, teaching students to have a global impact, because solving the climate is not something you do for Michigan, it's not something you do for Vermont, it's something you really do for the globe. And so one of my angles, the approach I have, the solutions I work on, is demand response, kind of like lights flickering. And so flexibility is something that's going to help the grid integrate terawatts of renewables. And so I think together with Johanna, we kind of played around with terms calling intelligent electrification. And I'll try to make the case that there are also something as unintelligent electrification as well. And so if you look across the US portfolio, energy systems, the grid is part of it, transportation systems, buildings, are sectors that are really key to make flexibility a reality and to integrate more and more renewables. And so as we electrify our end use, right, this means heat pumps, electric vehicles, we can start to consume those renewables. We can improve it with efficiency, so we need less renewables to solve our problems. If we take the demand and make it flexible, make it able to move with the renewables, we can not only absorb the renewables when they're here, but we can also help mitigate power system operational challenges, which is illustrated by the duck curve ramping effects. If you know what that is, you're in power systems. If you've never heard of the duck curve, one of the things that is really exciting to me is this topic here. So demand response today is basically what we saw earlier, right? Lights go off. It's a form of demand response. Turning off air conditioners in the summer for 4 hours, it's a form of demand response. Maybe you sign up for it, or maybe you opt out of it after you've been through the experience. But we have about 60 gigawatts of demand response today. Everyone predicts that's going to be 200 gigawatts, not of just demand response, but really flexible demand that can move in real time dynamically, basically like a control system. And so if you need to manage 200 gigawatts of flexible demand, you're going to need billions of devices. And how do you develop a control system for billions of devices? That's hard. And so what we need communication systems, we need control systems, and we need devices to be able to communicate. Luckily, connectivity is ubiquitous these days. Sensors are cheap. And so we can connect all these sensors together. We can bring them together so that every house, every city, every state, or every region looks like a big battery, acts like a dispatchable resource, right? And I could stop my talk here and say, hey, look, that's the solution. We're done. It's a pretty short talk. I could even tell you that, hey, it creates value too. It's pretty valuable. Flexibility can be quite valuable. Right? These are just very approximate numbers. The truth is somewhere in between. But that's pretty significantly valuable. If you buy a Tesla Powerwall, that's 5 kilowatts of flexibility. So that would be 5 kilowatts of flexibility. That's at least $500 to $5,000 a year that you can make in revenue being part of some program, assuming you got a good incentive back. There are lots of services that need flexibility today. That's why you see all these products. If you Google virtual power plant, you'll get a bunch of products. They exist today. I think earlier someone mentioned backup generators. So there's a company called Generac, the US biggest provider of backup generators, fossil fuel generators. They've invested enormously in batteries. Virtual power plants are now a thing that Energy Hub offers, Generac, Sunrun, and Tesla as products. But there are still challenges, right? We haven't solved the problem yet. Otherwise, I'll just leave now. Some of the real challenges we need to face is convenience and comfort. Right? Clearly, if you flicker lights, people won't be very happy, even if it, if you make $1 on it, probably not gonna be very happy. If you take a shower, a cold shower, because someone turned off your electric water heater, probably not gonna be very happy. So basically, you have human constraints. You have grid conditions and grid reliability acting as network constraints in your system. There are open questions around what business models, how do you manage risk across scales? And then a very important topic at which I do very little, and know very little, is cybersecurity and data privacy. Right? How much data are we willing to share? If you talk to banks and credit card companies, clearly people are willing to share anything. If you talk to general people, they tend to be pretty scarce about the data they're willing to let go. And so there are lots of questions around cybersecurity standards. I'm not going to talk about this today at all. All right, so going back to coordination, managing flexible demand, managing resources that sit in people's homes must require people. Energy today is fairly cheap. If you're part of a DR program today, demand response program, you might make $5 a month. Right? That means $5 a month. How much inconvenience are you willing to buy or sell at $5 a month? Right? A cold shower once, a hot apartment one time in the summer. At which point do you opt out of those services and basically stop being part of a flexible solution? And so statistics have been gathered on this. Right? Most DR programs, they bleed consumers every season. Turnover is pretty significant. And so there are lots of questions around how to actually manage these consumers, right? The people, the humans, they have certain needs that they expect from certain devices. And so it really is about what's called quality of service. Think of it like a constraint. It's a local constraint that every device has a constraint that if you want to engage this device in some kind of grid service, it has to first satisfy the human constraint. In 1982, going back in time, there was a service that kind of looked at managing the grid flexibly or managing resources. So at certain times of the year, an alarm would go off. And you could have then, before the alarm went off, you would have subscribed to a service from a utility that said, when the alarm goes off, I want 30 amp service, I want a 20 amp service or a 10 amp service. The lower you went, the more money you made. The challenge was that once it goes off, once that alarm goes off, the human had to run around the house and turn off appliances just so that the fuse wouldn't blow and they would lose service altogether, because that's a breach of their contract. And so you had a control loop with humans doing all the actuation, right? And today some utilities still do that using SMS. That's basically where we are in 1982, and it's not too far from where we are today. There's some more advances. But what I make the case for is quality of service is critical. And so what we need to think about is each device has a need for energy. Oops. In Vermont, electric water heaters is a big thing. Electric water heaters, everyone understands because we like to take showers, hopefully. And so electric water heaters work through what's called thermostatic control. Devices turn on when they get too cold and turn off when they get too hot. So they cycle between being lower bound and the upper bound. When they turn on, their device need for energy is desperate, right? They really need it really badly. And when they're at the hot temperature, the need for energy is low. They don't really need energy, right? What happens when you're sitting here or here or here? As the temperature drops, you're going to be more and more, have a greater and greater need for energy. The same principle holds for like an electric vehicle. How many hours are you going to be parked? How much energy do you need? 2 data points puts you somewhere in here, right? If you only have a few hours and you need a lot of energy, you're in a desperate need of energy, right? You might not have time to play part of any flexible electrification program. If you sit over here, you have multiple hours to just charge a little bit, no problem, you can wait, right? You can wait until the grid can accommodate you or until you can provide the service you need. Either way, you can compute the need for energy, right? You can come up with a scalar value for it. You can plot it. This represents basically your local constraints. Another way to think of it is that control schemes that manage these resources, they need to embed that need for energy into any of these algorithms, because the need for energy is a pretty simple mechanism through which you can prioritize which devices should be given access to the grid sooner. And the need for energy is not new, right? I didn't come up with it. It's a pretty basic idea that has been around for ages, right? The idea of incorporating some kind of energy need, like a temperature of an HVAC system, it's been around for a long time. And so some of the earliest work on kind of demand side flexibility is 1989, 1980. depending on who you talk to. So folks at Carnegie Mellon say the first work was 1979, and anyone who's not from Carnegie Mellon kind of focuses on 1980s. And so Schweppe's work is kind of the foundational work in demand side coordination and control. And the idea there was that you have your water heater or your air conditioner or whatever you have. There's a thermostatically controlled load. As the grid's frequency changes, right? When the grid's frequency goes low, you basically have too much load. So you want to reduce the load. And so you shift, when the frequency goes low, your temperature's deadband shifts, right? And you start turning off devices that may have a higher temperature than others. As the grid's frequency goes too high, you start turning on devices to kind of help balance the grid out in real time. And so they proposed this in 1980. The sensor needed to kind of measure this frequency accurately at 1 millihertz resolution was $60,000. As far as I know, 1980, there was no internet. So everything would have to be done through FM or AM radio waves. In 2009, this work was revived by a master's student at MIT, Brokish. He realized that if you keep everything with sharp corners, right, purely deterministic, you get synchronization effects, right? So when the grid moves here, you'll start oscillating around this point, you'll start having devices trigger on or off all the time. So you get a synchronization effect. So he added randomization into the switching to kind of mix things up. And in 2009, Ian and Duncan Callaway kind of worked on some air conditioning control problems. Johanna came along as well. And so the field since then has really exploded when it comes to demand side flexibility. You could do a whole talk just on what has been done. And here's just an outdated view of what the world looks like. It's, kind of our two main thoughts, or main control architectures. There's kind of a top-down control or broadcast-based control, and there's a bottom-up or device-driven control. I'll talk more about those in a second. Some examples for direct load control, which is kind of what's happening today. So direct load control scheme is basically when you broadcast out that all devices should turn off for some period of time, right? So a 3-hour event here. So here you have on the y-axis power, the aggregate power, total power from 2,000 electric water heaters in Vermont. A 3-hour event takes place where all devices turn off. What happens to the need for energy of 2,000 water heaters when they're not allowed any heating for 3 hours? I don't know. But they don't get hotter, right? They don't get hotter. And so what happens when you then allow them to come back online again? All these devices are going to synchronize, and you get this massive spike in power. So this is the morning peak. That's the bad control peak. What's that, 3x, 3 or 4x? And then you get this beautiful desynchronization because devices and people are all different. So we use our water heaters differently. Anyways, this reminds me a lot of like sprinkler controller, right? Go to Arizona, doesn't rain. Go to sprinkler in Ohio. Sometimes sprinklers run right after the rain because we didn't adapt them or do anything dynamically. And so what has been happening is there's been a lot of advances, especially on the academic front, but also I think in industry as well, on kind of how to manage distributed energy resources, so DERs. And so one architecture that's used quite a bit is broadcast-based or top-down coordination. In these schemes, the coordinator can send control signals to a whole fleet of devices. Those signals could be really simple, binary values. They could also represent a distribution that tells you the likelihood of a device moving from on to off or off to on based on its need for energy. Right? So you're going to have certain transition probability. Maybe there's a 30% chance that a cold device switches or 80% chance that a hot device switches. And so you can design control policies, you can design models, you can do all kinds of cool stuff, and Johanna has done that. Or a lot of people have done that as well. And so one of the kind of the key parts of broadcast-based methods is that when you send out messages, you may not always know what the devices are doing. And so if you want to build feedback loop around here, you need to kind of know which devices participated when I send out the control signal and which did not. If you have estimation capabilities, or you have a significantly large population of devices here, then you could infer that from like a substation or some grid measurement, one point, or a grid measurement, a point of common coupling between the grid and some other element. And so that feedback signal can be quite hard to get in a broadcast-based scheme. The other things that are hard to get is to know, if I want to send this signal out, how can I hit controllers that sit in different parts of the grid? Maybe different parts of the grid needs different signals at different times. And so how can I take into account grid location? And what if devices cycled recently? How do I take cycling into account? The fact that some devices may be worn out from having participated recently and others are available already. So these local constraints are harder to gauge when you're in a broadcast-based scheme. What I'll focus on today is what I call, or what's denoted a device-driven or a bottom-up coordination scheme. And so in a device-driven scheme, we don't broadcast the control signal out that maps to the device's need for energy. What we instead do is we essentially put a control policy at the device itself. Put a control policy at the device. That control policy maps how the device will interact with the coordinator based on its need for energy. So the higher the need, the more likely it is that this device will ping the coordinator and say, hey, I'm available, do you need me? A hot water heater doesn't need to interact at all with the grid. So why do we need to, so we don't need to communicate at all with it, so it'll just stay quietly. It's not able to participate. It has no priority. Devices that get colder and colder will have a higher and higher need for energy and will interact with the controller or the coordinator much more frequently. And so instead of broadcasting out signals, you can listen to the devices requesting their availability in real time. This implementation is asynchronous, which means devices can ping on their own time. So you kind of move from a continuous time spectrum to really an event-based spectrum. So fairly light communication. The other things that is quite valuable is because the devices request access and you then accept or deny their access, you can keep track of which devices have been accepted and denied access. If a device keeps getting rejected or denied, it can opt out. It can say, hey, screw you, I'm done, right? I'm just going to go and turn on anyways. And so it can ping, it can communicate and say, hey, I'm going to turn on anyways. Essentially, it's taken up that portion that the grid needed or grid had available, and it does so for a short amount of time. The other thing that these requests can embed are certain device level behaviors. If a device has wear and tear, if the device has cycled recently, you can build that into the requests. And so you can deprioritize devices based on local behaviors, local requirements, or even grid conditions. So the ideas behind device-driven coordination that I'll share today is the topic is called packetized energy management. And this is a device, we hear at a company called Packetized Energy, so it's a very creative name for a company. And we basically borrowed two ideas from how the internet works today. On the internet, we have packetization of data. Data is shipped across broadcast networks at very, very high speeds, right? Data is sent across as small data packets, right? The video that's streaming now is not a big video chunk going through the internet. It's a bunch of small packets. And then you have lots of control schemes on the grid, random access protocols. And so we're going to try to build these ideas into how to manage a set of resources on the grid. And then I'll show you kind of what we did. So these are more like mechanisms. And I'll show you how it worked. And then I'll come back and talk about models. And then the last M I couldn't figure out. So I stopped. I didn't make the title, mechanisms, models, and something else. All right, so consider, again, the need for energy. We've discussed it, right? Water heater, we know. This is standard water heaters. 20 minutes of heating, right? And water heater gets cold, it'll heat up for 20 minutes. If you have a lot of water heaters, it's a lot of 20-minute heating needed. You could packetize the water heater. That heating demand could be chopped up into 4 or 5-minute chunks, right? Small chunks. You can deliver that heat. If you do it in a smart way, you can offset the packets ever so slightly to align them with the availability of renewables. Maybe there are times when the grid is cheaper than other times, when the energy is cheaper, I mean. And so you can effectively have the devices request these packets based on their need for energy. And by offsetting them in time, you're essentially creating a system where devices will request a packet, and you accept or deny them or not. And you can, this exchange between devices and the coordinator can happen in real time. We've extended there are lots of papers on extensions to electric vehicles and extensions to batteries as well. and recently to HVAC systems with Johanna's group. And so the key part here for packetized energy management, the approach we've taken is that between the temperature limits of the water heater, these are in Celsius, you have essentially a mean time to request that is proportional to the temperature itself. So the colder a device gets, the more likely it is to make a request. This basically allows you to dynamically prioritize which devices will request first or more frequently than others, which means that when you then have some capacity that the grid can hand out, you can give it to the devices that have, on average, a higher priority. So it effectively is a dynamic prioritization scheme. And if you then implement this at scale, not just one device, but you implement it at scale, you can see that if you start with a system where supply does not meet demand, right? You want to shift your demand to match the supply. Maybe the supply is uncontrollable wind. You can take your load. Some of it is more flexible than others. These gray blocks are inflexible loads, non-flexible loads. And these blue boxes are packet-sized loads. But they haven't been shifted in time, haven't been coordinated at all. And so if you do randomization and packetization, and you coordinate using packetized energy management, you can link up your supply and demand. You're basically shifting demand. Another way to think of this problem, so we actually looked through the literature, and folks solving kind of these packet-based or dynamic prioritization problems would tend to do optimization-based schemes. And so you could imagine scheduling a bunch of these packets into the future and then hoping that your forecast was good. And so this approach effectively solves the scheduling problem in real time, of course, not guaranteeing optimality, but solves a really hard problem in effectively real time. And so you can close the loop, right? We have our coordinator, we have the devices, we have a request stream that comes in here. It's asynchronous, so this is essentially a random process. And you have feedback, you have control. And so the key control mechanism is the average rate at which you say yes or no. So as devices come in, you essentially modulate the acceptance rate. And as you modulate the acceptance rate, you're effectively tracking some reference signal. And the idea is to drive the error to zero. And so one of the first things that students in my group worked on was really building a simulator to kind of see how things work at scale and explore various, academic laboratory setups. And so the blue signal is kind of what the grid needs, and the red signal is what the devices are delivering. And here you have a histogram of everyone's temperature. These are 5,000 electric water heaters simulated. And you can see, A, we track really well. B, the range at which we're tracking is quite significant. So we're looking at up to 3 or 4 megawatts. And throughout this process, the distribution of the temperatures stays relatively stationary. It's just a simulation. With RPE, they basically asked us to not just simulate it, but implement it. And so in 2019, we have a student, Adel, he worked very, very hard on making this happen. We had packetized the company, and we had fabulous partners, utilities, transmission companies, and the university, helping us deploy this technology in 150 homes in Vermont. So we had 156 loads running packetized energy management scheme, the algorithms we built, to deliver this grid service. It's a lot of work for like 2 hours of demonstration. But it worked, right? You can see it tracks the red signal, tracks the blue signal fairly well. It met the specs at least. And so RPE was very happy. So then RPE the funders came back to us and said, hey, go faster. Instead of this minutely stuff, can you deliver frequency regulation? And so we spent 2 years kind of pushing technology further, working with the startup company and deploying more devices into the field. And so in December 2021, I was sitting in Denmark on my sabbatical. We had run a number of tests. Each test was 2 hours long. We did it 4 different days. And so the signals that we're providing, the frequency regulation service is one that's called pay for performance. So the better you perform, the closer to 100% performance, the more money you would make as a grid service or as a resource. And so on these days, we performed around 90% consistently. The exact calculations are always complicated because I don't really trust the resources we had for it. But we were always around 90%. So calculating these is tricky because there's no real references for them. And we had some disagreements on exact, I think the digits over here were different. But the key point is this: we scored about 90% on 4 different days. That's better than the average performance of the independent system operator, PJM. So the average performance is around 80 to 90. So we scored our resource, which is an academic byproduct, implemented in a startup company's platform, scored better than the average of current generating assets across the Midwest. We basically outperform most assets on the grid except megawatt scale storage, which can basically hit the 100% because they're power electronic based and they're super fast. And so we implemented this. RPE was happy, hung out with Johanna's group and Leke and other people. And we extended their ideas here with from water heaters, electric vehicles, and we added air conditioning loads. And so Leke did some nice work, kind of pushing a new mechanism that kind of allowed the devices to not just turn on, but when they're on, actually request to turn off again. And so with the work, with the collaboration in Michigan, we showed that the performance can improve significantly between original vanilla packet size management, which is kind of what I'm presenting you so far, and kind of this new version, which I guess is strawberry. It's better than vanilla. And so the performance improved quite significantly in simulation. I don't know if there's frequency regulation results that are happening, but it was very promising. And it's pretty cool. Simple little mechanism with a pretty big impact. It's cool research. Anyways, so what I've shown you so far are mechanisms. I've shown you some results. I haven't really shown you any models. So I thought maybe let's dig a little bit into the models. Yeah. So when you work on the topic of flexible resources or flexible demand or distributed control of DERs, a couple of things that are quite interesting. One area you could focus on is basically if you're using people, right, as people's home, people's devices, people have certain behaviors in which they interact with the grid or devices, right? You take showers at certain times of day, the way you like your air conditioner set up, occupancy, other things drives basically the background demand. To model that is hard because individual people are very hard to model. Fleets of people, much more manageable. So we have done some work based on understanding what does the stochastic behavior look like of humans in the loop. Because this is essentially a background disturbance. We want to model background disturbances. Once you then take that background disturbance into account, you build a model of your fleet. That model is going to look like a battery, except the parameters are going to be uncertain. So it's like operating with a stochastic battery. Right? Imagine battery, you don't know the state of charge, you don't know the capacities, you don't know the capabilities exactly. So you have an uncertain resource. And so there's some interesting problems around dispatching uncertain resources. And so we've been working on that. I'll skip that today and I'll just focus kind of on some basic modeling and relatively basic, and show you what we use the models for. And the modeling are really just supporting kind of the study of the PEM fleet, because it's not a model-based approach. Like we're not modeling. Everything you saw was basically a live asynchronous implementation of the algorithm, the mechanisms. What we want to understand is kind of what are the limits to that mechanism. How much can they deliver? What can they not deliver? And how do you best position the fleet to deliver what the maximizing profits, basically. All right. So a general fleet will have devices that are in standby that can make requests. Right? There could be batteries, there can be charging requests and discharging requests. A device that gets accepted moves over here to this charging fleet, charging population. If it's a discharging, it gets over here. When you're over here charging, your state of charge goes up. When you're over here, your state of charge goes down. Every time you accept a packet, every time you get accepted, you essentially get added to a timer. And so PEM has essentially the population dynamics, but also timer dynamics, right? And the timer runs and the devices exit the timer at the same time. If devices get uncomfortable, desperate need for energy, they opt out. And so you can model that. And again, transition can happen from any path along here. Sorry, transition can happen from any path along here to charging or discharging. And so you can model these transitions fairly straightforward. So it's a controlled Markov chain, M being the dynamics of the devices. So there could be water heaters, it could be air conditioners, electric vehicles, or batteries. And so they have certain rate at which they move up and down, which their state of charge changes with time. The dynamics basically are the autonomous dynamics. And then you have the control dynamics, where beta C is the rate at which the, well, I guess I can just next button. So devices that complete their packets, they move from charging to standby. Devices that start, that's the rate at which we're accepting devices. They move from standby to charge. And you have the other transitions. Transition from discharging back to standby and from standby to discharge. And so this is effectively the proportion of devices accepted for discharging. So beta C and beta D are the control variables. The outputs is the aggregate power, charging minus discharging. And then you have the request, the total number of requests from each. Right. Total number of requests coming in from your standby fleet for charging and total number of requests for discharging. For their batteries, for example. And you can see here that this model that I'm implementing does not have any opt-out mechanics. And so what happens if you set betas to 0? Like if these beta Cs and beta Ds are all 0, then there's no way to transition from standby to any other mode. And so the device will just get higher and higher need for energy until they eventually accumulate at one of the bins. And so that's, of course, not acceptable. And so you create the opt-out dynamics with that in mind. And so you can test the validity of the macro model in a simulated environment. And so these are, to be fair to ourselves and everyone else, these are homogeneous models, right? This is, every device is exactly the same. Every single water heater is exactly the same. And so when you implement your model, you have a period where you accept everything, and then you turn everything off. You accept you only accept charging here, and you only accept discharging here. And that's basically like a step response for the fleet. And you have, so what happens? The state of charge, when you accept everything, the state of charge, average state of charge is here. And when you discharge everything, you discharge your fleet down until some steady state. You can see here the models are able to accurately capture the specific temperature bins, right? So these are the bins in standby. And during the deny all period, you can see that we also capture the steady state conditions quite well. There's some cool things you can do with this model. One of the things that we looked at is kind of this, there's this term, the completion rate, beta minus. Beta minus is a pretty nasty nonlinear term, deals with a timer, deals with the states. And so, So what we could do analytically is you can basically say at steady state, what does beta minus look like? And you can show that at steady state, beta minus always takes on this roughly constant value of 1 over the number of timer bins. So the number of timer bins here would be 0.05. And even though we're not at steady state, that timer bin is pretty close to 0.05. Beta minus over here is basically exactly 0.05. And so that's once we did the analysis, we can kind of see that, hey, that beta minus being constant is not a bad approximation. Get a pretty good model still. So we've used that in the past to simplify analysis. The other thing we like to answer, or the other question we like to answer is, what's the minimum constant power that a fleet will consume to satisfy certain consumer quality of service requirements? And so we call that the nominal response. And so in the nominal response, you can set beta equal to 1 over NP. You can then have an optimization problem that's nonlinear, but behaves very well. So you can find good solutions rapidly that describe basically what is the total power that the fleet will consume and the control point, the control beta, so the beta stars, that'll achieve that constant power, which is a great way to initialize simulations and a great way to understand baseline demand. We also went a little bit further to understand the behavior of the system by, instead of modeling the individual bins, kind of modeling the entire system. And so we call it a virtual battery, virtual energy storage, or energy-based model. And so we really wanted to reduce the number of terms or states. And so we're just considering the timers, the total number of devices opting out, total number of devices being on, and the average state of charge for the fleet, because that gives us a sense of how much flexibility we have left. And so for the sake of time, I'm going to skip these slow introductions. So average state of charge basically looks like a thermostatically controlled load with some end-use consumption here being a stochastic parameter at scale, thousands of them, that behaves fairly well. And so that's is a mean value. Number of on devices has certain dynamics, right? The total number of, oh, it should be K plus 1 here. Total number of on devices is on plus what opted out minus what's completing from the timer. The total number of requests is basically the probability of making average probability of making a request times the total number of devices that are off, which are the ones in standby. And so you can kind of go through this whole thing, the total number of consuming loads, the timer states, and the total number of opt-outs is the opt-out dynamics. And the opt-out dynamics are basically two parameters, A1 and A2, which we got from some regression analysis. And so the regression analysis pairs these two parameters with the total number of denied requests. So the more you deny requests, the more your number of opt-outs will increase, which also kind of makes sense. Lastly, we had to constrain behavior of the input. Beta, this beta, can only be between 0 and 1. And so you have to constrain that, which means you have a constraint on the input as well. So that translates. So this constraint to 0 and 1 translates into this constraint. And so you can have this low order virtual battery model. You can model it to optimize like an economic dispatch, looking out multiple hours. You can say, if my winds patterns or solar patterns or markets look at a certain way, how can I optimize the trajectory of the fleet? And you can see here at time 0, we start with some initial distribution, and we basically forecast what the fleet should be doing over time, which gives us the state of charge trajectory. And we'll then basically drive the system to a final distribution that satisfies certain constraints. And that constraint is a terminal constraint on the optimization problem. It's a nonlinear optimization problem because the probability of requesting is nonlinear. And so we're moving, clearly the state of charge moves a lot. And so you have to solve a nonlinear program. Julia can do it. It took 7 seconds to solve this problem. So definitely useful for analysis purposes. Another case we implemented, packetized energy management has a pretty poor down, what's it called? Oops, down. So it's a ramp limited system. So it's unable to basically reduce demand because we have water heaters, you can't turn them, you can't make them inject power, right? You can only make them turn off or consume power. And so they're really down ramp limited. And so if you want to provide a grid service, when that signal goes down, you would love to act earlier than necessary. And so we built a precompensator based around the prediction model. And so for frequency regulation, there are certain things that work in our favor. The signal, regulation signal is energy neutral, which means that the state of charge doesn't move a lot. If the state of charge doesn't move a lot for an energy neutral signal, it can linearize really well. And we basically built a forecast tool for forecasting frequency regulation signals and showed that that works pretty well 20 to 30 seconds out. If it worked 5 minutes out, we'd be millionaires. But that's the packet length. That would have been awesome. But 20 to 30 seconds out means you can still make certain adjustments to optimize performance relative to the metrics of the grid itself. And so this precompensator works really well. You have the forecasting, you have the control, all of which encompasses the PM scheme together. So that's some of the model use. The other thing that I think is pretty nifty, and this is a bit of a mechanism, not really a model, is the going back to Schweppe. So Schweppe decided that you could regulate demand based on frequency. And so if you were to plot your timer over time, or plot the timer versus temperature, what you get are basically two marginal distributions. One, the distribution of your timer states. One, the temperature distribution. This one, the coordinator has full access to, right? The timer states are fully observed. The temperature states are not. I don't know exactly what the temperature of the fleet is at any given time. I don't know what the timer states are. And so if I could interrupt packets, right, as the frequency, if I can at each device implement a little control algorithm, like a proportional controller that says when my frequency deviates, I interrupt the device based on where it is on the timer, not the temperature, the timer. And so I can devise a control scheme that in aggregate starts interrupting packets based on local device measurements. And so this is very similar to Faber, except that we don't interrupt on the temperature, we interrupt on the timer state. And the timer state being fully observable means at any given time, I can estimate exactly, because I know the distribution, and I designed the control law. And so I can convolve the two, and I can know exactly at any given time how much responsiveness I have to offer the grid, right? So if the frequency deviates, I can basically, given what I know in real time, my timer distribution, and the control I designed myself to interrupt each device at a certain threshold, I can estimate in real time what my response will be to a given disturbance on the grid. And so we think that that could be valuable if the grid operators are interested in kind of fast frequency control resources, because we could then offer that in real time. Right? So I think synthetic damping is something that's been discussed. And so we can estimate that in real time. We've been looking at some of the trade-offs between frequency regulation, offering AGC services, and then synthetic damping. So the more you offer in one, the less you have available for the other. All right. So I have 2 minutes left, or 1 minute left. I have some interesting work I'm happy to share on what role the grid operator should play. Right now, we haven't talked about the grid at all. We played around with packetized energy management, thinking through, essentially, can we combine grid measurements? Think of them like logical gates, right? If a grid is overloaded in one location, devices associated with that location will not make requests. And so you can have certain sensors around the grid, essentially acting like traffic lights. And so when a grid is overloaded in one location, there's a red light, and red lights don't make requests. And so you could basically think of congestion control or congestion mitigation as a bunch of traffic lights. We've shown through simulation that this works fairly well. Haven't done a lot of analysis on this yet. And so we've shown, that vanilla PEM versus the grid-aware PEM can really mitigate effects of overload in distribution feeders without really sacrificing performance. Performance meaning the grid service you're providing. Okay, so I'm gonna jump to the end because it is the end. And so I'm happy to share those discussions, grid discussions at a later time or different time. And so some of the new things we're working on in Vermont are kind of moving from virtual storage, virtual batteries to really physical batteries. And so we're building a test bed to validate control and optimization algorithms. This is a new project kicking off right now. We're looking at hydrogen fuel cells, lithium-based batteries, solar facilities, thermal electric optimization and control. So we're building a hardware test bed over the next 4 years to validate control and optimization algorithms related to hybrid energy systems. We've been given some swanky lab space, we have a decent sized hardware budget. And we know from DOE that this topic is becoming pretty interesting. So what role can hybrid energy system play? It's kind of like microgrids, combining different types of energy resources. So we're looking at long-term planning tools, taking into account degradation economics, short-term operations, and then thinking about how workforce development can be enabled through this platform as well. It's only 100 kVA microgrid, but it's still significant. And then as usual, there's stuff I didn't talk about today, which is fun. Fun NASA project where we got to do optimization outside of the grid, which is fun. Some network reduction techniques, multi-energy systems, and then different methodologies for characterizing energy transition. What are salient features that make up these algorithms? And so I apologize for skipping a portion of the content that I really wanted to talk about as well, but I think you got a sense of what I do. And so I look forward to kind of taking traditional demand and turning it into something a little more modern. And so, yeah, thanks for the opportunity, and happy to take questions.
Otherwise, I'll point to students and you have to opt.
Is there still a rule that students have to ask questions? Otherwise, there's no leaving.
So you probably explained this or alluded to it and I just missed it, but so you're doing energy management in a packetized form. What happens if you take the limit as the packets get arbitrarily fine, arbitrarily small? Like, does the problem get easier in the limiting case?
So the packet length, the smaller you make it, the more fine and granular the control is, the better your bandwidth for control is. So the smaller the packet length, the better your system will perform, with the caveat being that you have more communication requirements.
So is it safe to say that as you go forward into the future, there is a motivation to make packet length shorter as bandwidth improves?
So assuming devices are, so the devices you're switching could be a compressor for an air conditioner, in which case you can't switch it very, very fast. And electric resistive water heater, it can handle a lot more cycling than other types of devices. Electric vehicle chargers, power electronics have certain requirements. So I think the ideal would be the bigger the packets, the less wear and tear on devices. And so how can you do more with longer packet lengths? Also lower communication overhead. That'd be the holy grail, I guess. Yes, Johanna.
Just to follow up on that, though, an element of a packet is also how much power, right? So if you're switching it out and off, then it is whatever it's rating. But if these things all have very power draw, then you're also choosing that, so you can make that much smaller.
That's true. Yeah. So we have
trade-off with the efficiency of the device, but it's going to be efficient at different points.
Yeah.
Right?
Yes, we did some work with heat pumps. This was variable heat pumps that had different efficiencies. And so for the simulations, we just used standard packets, which just had a fixed coefficient of performance. But the simulation, you could really ask questions around. You can change the height of the packet and the length of the packet. But we haven't really played with those parameters.
So maybe related question is, are you saying each device have different shape of this packet, or in your current simulations, there's a standardized?
So in our simulations, the models we used assume a fixed packet height. If you had different packet height, you can group them together in different groups. And so we've done some work looking at kind of the grouping effects. But there's, in the simulation environment, the mechanisms would work across any packet size and packet length. You can mix and match them. Just quantifying performance is a lot harder.
So for the network aware PM, what kind of information is shared across devices? Do you have like the architecture of the network?
That's a very good question. So the architecture is effectively hiding here. So the assumption that there are pretty cheap chips that you can put that can measure voltage and frequency. Like there's also micro PMUs and other expensive assets you could use. There's SCADA assets. The assumption here is that grid measurements, either directly or as red light, green lights, make it to the coordinator.
Do they have to reach only the coordinator or the devices as well?
Either one is possible. Our thinking is that you want the coordinator to essentially have a red light, green light traffic map of the grid, and devices coming in pertain to certain nodes in the grid, which have the red light, green lights.
Okay, so that would basically entail the system operator communicating this information to
the system coordinator, the grid, the utility would effectively send updates whenever signals changed, and the aggregator would then have a red light, green light view of the grid. That's one way to do it. The other way is you could have each device be aware of its logical gates. And then if any of them are red, you block requests. Different architectures are possible. There are trade-offs.
Can I just follow up on that? There would seem to be an equity issue that if my neighbour is charging his electric vehicle, I can't start it for him.
For 5 minutes.
Yeah,
So yeah, that's distribution grids are inherently inequitable because they are tree structures, and trees they have leaf nodes, and when you're at the leaf node, you're at the mercy of everyone else. So it is quite inequitable. So the packetized scheme in that sense essentially would rotate people around. So you would get your 5 minutes of charging, and then you would come off, and then if someone else is more desperate than you, they'll be more likely to request, and then they would be the next in the queue.
so they pay more for the privilege of getting a higher priority.
Theoretically, you probably could do that. We haven't played around with those schemes at all. You certainly could. I think, yeah, we played around a little bit with it for some peak events. So we pre-selected devices that were more desperate than others, and they would get first access to the little slice of demand that we set aside.
So for at the beginning, you mentioned that you're going from 700 devices to
900,000, almost a million. Yeah.
have there been any requests about incorporating this kind of network awareness to your control?
Not in a dynamic environment. So there has been questions around electric vehicle charging and whether electric vehicle charging are going to overload certain feeders or certain transformer substations. And so using historical data, we've done some consulting jobs for utilities showing how much capacity they had at certain substations. But we didn't implement controls for it. But it's, yeah, we haven't played. This is more academic. This was not implemented.
Any last questions? Jim looks like he wanted to ask a question. Oh, no, right. No, I was just my glasses off.
I just want to know what the beer knowledge, but it's not this one. But you had beer that.
Oh, yes.
Don't want your beer to go.
No, it's no. So demand response is $5 a month roughly.
Yeah.
What can you get for $5? So in Ireland, they call it the 2-pint problem. Because for $5, you get 2 pints. And so how much work are you willing to do for 2 pints? Inflation, right? We came up with the Fenway-Frank problem for the Boston communities. In Vermont, we call it the creamy conundrum. Yeah. So it's based on quantifying how much work are you willing to do to be part of a human-driven demand response program. So I really struggled. I tried to come up. I asked friends and family, like, what do I do with Michigan? And Zingerman's is not. This is a tough one, right? Because they're like $15 for a sandwich.
Colors gets you a Zingerman's pick, maybe.
There you go. But it doesn't zing, you know. It's
gonna have to work harder on this dynamic response being profitable, right? Sandwich, I might buy into it.
So if you respond, you get a Zingerman sandwich sent to your door.
Get a probability of having a Zingerman.
That's right. So weighs the pros. When you have to participate a lot, is more likely.
Okay, great.
Thanks, Ian. Kind of wanted to show this, but I ran out of time. Something had to be cut. So this is that was the convex inner restriction, the convex restrictions.
Okay.
So it didn't make it. But there you see it.
Only 50 minutes.
Yeah, so you see, it's quite nice. It works really well. So here you have the upper bound, the lower bound, and then the realities in between. Same here for different load conditions.
Oh, yeah, I really like your talk.
Thanks, Jeff.
I wanted to ask you, Really quick,
That's pretty fun.
Thanks.
It's two interesting power plots in a row. In the Draguno.
Yeah.
Here's another one. One's better figure it out.
is there a reason why you can't apply these same techniques and problems where you have significant reactive power, where you